Okay, we're starting with 25 students today. And the section A, C, A, so you are B. So you are always like you don't come all students. You can always look at your previous what is the videos of your friends. Anyway, so this is the single phase rectifiers. We have already started these things before our break, if you remember. Did I start that one? Okay. Before the break, probably you have forgotten everything. So this is the figure of the single phase. In the single phase thyristors, converter control rectifier with LSC capacitor. We don't have any LS here. There could be LS here, but this LS equal to 0. And also the load we are considering here constant current. So if we plot that, if this is your IDT, then if we plot it, IDT, just a parallel, okay? And the peak value of this one, or the value of this one. So this is your load current. And with that one, we have already covered before the break to remember that how it will work. So I am repeating this one. Okay, let us go back to our whiteboard. That will be easier for me to make you understand. Okay, so this is your rectifier. Control rectifier, of course, because thyristor can be controlled. And we call it phase control because the thyristor will be controlled with respect to your input voltage. So the input voltage is sinusoidal, and this will be your √2 Vs sine of omega t. So if this is your input voltage, this is your pi, this is your twice pi, and 0. So the this peak will be your √2 Vs. So you can fire this thyristor. This is your T1, this is your T2, and this is your T3 and T4. Can you listen to me? Someone must open your microphone. Yes, you have to say yes, sir, no, sir. Otherwise, how can I know you are listening to me? Okay. So this is your load or DC side. Load we have taken as constant current load. Constant current load is represented by current source ID. So this T1 and T2 will be fired. Maybe you have the choice to fire between your 0 to pi, and also T3 and T4 will be forward biased between pi to twice pi. Let me write down. T1 and T2 are forward biased. Okay. And T3 and T4 are forward biased. Okay. Pi to twice pi. Now tell me, what is your magnitude of your source voltage between 0 to pi? You have to interact. What is the voltage? What is the voltage between 0 to pi? Is it positive or negative?
Positive, sir.
Positive. This one, look at this one.
Yes, sir.
And pi to twice pi, look here, it is negative, right?
Yes, sir.
Okay, so with that one, we can say that T1 and T2 will be forward biased between 0 to pi, and T3, when it will reverse the direction, we can say that T3 T3 and T4 will be conducted, that means they will be forward bias. So we can apply the firing pulse maybe here. This firing pulse with your IZ T1 and IZ T2 that will be fired here alpha, and we shall also fire here pi plus alpha, and this will be your IG3 and IG4. And then we see that between 0 to pi, although T1s and T2 are forward bias, but since they are not fired, so they should not conduct. Okay, so the conduction of the thyristor T1 and T2 will start from alpha. Okay, so let us draw the output current omega T equal to from 0 to infinity where you want to go. So this will be your ID, this is your IDT. This is your IDT. Now, so this is your alpha, this is your say pi, and this is your say alpha, right? Your pi. So 0 to alpha, we will not consider right now. Let us consider after omega t equal to alpha. So T1 and T2 are forward bias after omega t equal to alpha, then current should, this IS current, let us plot this IS current here. Omega t and IS. So IS current will be, look here, IS current will be, let me use another pen. IS current will be this one, this one, this one, this one. So this IS current will be same as your IDT. IDT and which is equal to your capital ID. So we can plot this current, this is your ID, right? And then at omega t equal to pi, although the voltage will go to negative after omega t equal to pi, but we have not given any pulse to T1, T3 and T4, so they will not conduct. But we must, our load is such that it must carry the current, since the highly inductance is there. So that current will force this T1 and T2 to conduct until T3 and T4 are fired. So then this is your alpha, this is your pi, and this is your pi plus alpha. So it will conduct. Can you see the figure?
Yes, sir.
Okay, so now at omega t equal to pi plus alpha, the voltage is already reversed. So T3 and T4 are ready to fire, ready to conduct. So we have given a firing pulse here. So then the current will start flowing this way, this way, this way, this way, this way. In the load, it will be the same direction, but T3, T4, and it is coming back. It will go T3, 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 and from through your T4, it will come back in the opposite of what we have seen for this one. This one is the alpha to pi. So then after that we have seen that current has reversed in direction IS. All same magnitude of current will go, but it will reverse this in the direction there. But again here we shall, this is pi, twice pi plus alpha. We will apply this pulse here, that means this pulse here. So until that, your T3 and T4 will be conduct. So this one is the twice pi. This will be twice pi plus alpha. This point. So during this period, look here, T3 and T4 should be conducting. T3 and T4 conducting means that we will get the negative current here. So here also, T3 and T4 will be conducting. It is similar to your here. That means twice pi plus alpha. That will be equivalent to your 0 to alpha. So, and we will get that negative current. Okay. Now, when T1 and T2 will be conducting, then your output voltage, say output voltage here, T, that will be equal to your Vs. So, same concept from your diode. So, this will be Vs. And still T1 and T2 is conducting here. T1 and T2 is the conduction here. This is your T1 and T2. So you will get this voltage, input voltage. And we have seen that since the voltage is negative and T3 and T4 is fired, then shifting of the current will go from T1 and T2 to T3 and T4 immediately at pi. This is the pi plus alpha here, and this is your alpha. The shifting of the current will be occurred at the point of firing, and also the output voltage will go to your PS. So, and if it come here like this, so it will be just replica of this one. And we have already done these things before our midterm. Can you remember this? Hello, people, my dear students. Can you remember this?
Yes, sir.
Okay. So now let us go to the book again, because these are the repeating things. Before the break, you have forgot. So this you follow my pen. So this will be your input voltage. Okay, this is your input voltage and your VD. Okay, and if you fire your thyristor, you have to answer this question to me. If you fire here, this is your IGT1 and IGT2, that is alpha equal to 0, and this is your you are firing here, say alpha equal to pi, then what will be your wave shape of output voltage? Alpha equal to 0.
Sir, it's the VD that's shown in the upper figure.
Yes, it will be just like your diode rectifiers, right?
Yes, sir.
Oh. Now, let us go to the next figure here. Look here, now we have applied the firing pulse at omega t equal to alpha, that is maybe say 30 dB. Then, as I have already shown you, the output voltage will look like this one. You understand how we will get that? Yes,
Yes.
or no? Okay, that will be the output voltage. Now, if we integrate this one, we get that average value, VD average. So we will call VD alpha or V average. So VD alpha or V average, or sometimes we call it V4. That will be your 1 by pi. Then alpha to pi plus alpha. That means we can just integrate repeating cycle. So that will be root 2 Vs sine of omega t d of omega t. Okay. And if you complete this one, you will get 0.9 Vs cosine of alpha. So now we are getting the controlled output. What is the controlling parameter here?
Alpha.
Alpha. So what is the range of angle of alpha?
0 to pi.
Exactly 0 to pi. So if your alpha equal to pi by 2, then what will be your average voltage?
0.
For cos 90 degree pi by 2. Cos 90 degree how much?
So cos 90 degrees 0.
0.
Sorry, 1. Yes, sir. Zero.
Output voltage is 0, right?
Yes, sir.
So look here, why? Because this is your alpha now, and you will get the, so this portion and this portion will be look equal. So positive area and negative area will be equal, then average voltage will be 0. You got my point or not?
Yes, sir.
Okay. Now, this is your voltage. Now let us talk about the current, output current. Output current is always constant. The input current I have already shown to you in my whiteboard. So output current will have the wave shape. Change the color. Like this. This is a look here at alpha. This one it is mentioned T3 and T4. T3 and T4 is conducting. And from here to here, this is your pi, and this will be your pi plus alpha. So T1 and T2 will be conducting here. So T1 and T2. And then, as I mentioned that, so you have applied the firing pulse here at pi plus alpha to your T3 and T4. So from here to here, they mentioned here already T3 and T4 will be conducting. So you will get the negative part. So we are getting the rectangular shape of our input current. This is sinusoidal. Rectangular is not of course sinusoidal, right? So it will contain lot of harmonics. Am I correct or not? If we
Yes,
do
sir.
the Fourier series analysis. So what will be the even harmonics?
So 0.
Even harmonics will be 0. So we can analyze these things in the data figure. So did I not cover all these things before break?
Yes, sir. I think this part was covered.
Okay, so I am just repeating for you. Okay, you can look the equation number 6.6. This is nothing but voltage wave. And later,
Sir, could I ask a question?
yes,
Sir, could you go to the above figure with the source voltage and source current? Right, sir. So, right, sir. The bottom one, right. Sir, from pi to pi plus alpha, the source voltage is negative, but is that right?
yes, you are correct. Source voltage is negative. Okay, then what is your question?
Sir, is that not problematic for the source that the voltage is positive but the current is negative? Because both of the parameters are from the source itself.
Voltage has already reversed direction.
Yes, yes, sir. Voltage has already reversed.
That means
But-
negative voltage, and current is also negative. But here, okay, you are correct. The voltage is negative, but the current is still positive.
Yes.
Current is positive, the voltage is negative. No, what is the problem? What problem do you expect?
Sir,
So
they
it
are
is the
180-degree phase apart, the current and the voltage.
which current and which voltage?
Sir, the region that he has just mentioned. So the current is positive and the voltage is negative. Sir, aren't they 180-degree apart?
They're apart because of the firing of the thyroid. Right?
Yes, that's the reason, isn't it?
Okay, So this current IS is negative because you look here, although the voltage has changed its direction, it has begun gone to negative, but still the current is flowing like this because T3 and T4, sorry, T1 and T2 will be conducting here. Our load is such that the constant current. So where this current will go? Tell me. Where this current will go?
Right, it will force itself through T1 and T2.
Yes, exactly. Although the voltage is negative, this is the essence of the power electronics. The device will not be stop conducting, although the current voltage will voltage makes the device reverse bias, but still, since there is no path, so current will force the thyristor to turn on, and current will be flowing through this one. You got my point?
Yes, sir, that happens and that's okay, but
yeah, okay. Now I am telling you. Okay.
right.
So this your instantaneous voltage is negative. That's true, but average voltage is negative. Our average voltage is this one. This is your instantaneous voltage, right?
Right, sir.
So average voltage is negative or not? That's main thing. Average voltage is negative because this area say this is
Sir, ID. Sorry,
okay.
sir, ID.
No. This area is B,
right,
and this area is A.
Yes, sir.
So
average voltage is positive. Yes.
Yes, average is positive, and current is still positive. Look here, current is still. So what about the direction of the power? If it is positive, positive.
Yes.
That means it is absorbing. It is still working as a rectifier, no problem.
But so for that instant, for those that moments where the source voltage is positive and the source current is negative, that means that the it's going the opposite way.
No. Source current is not negative. Which where?
Sorry. I think the opposite. The source voltage is positive. Sorry, negative, and the source current is positive.
Yes, right. But yeah, instantaneous voltage is negative.
And that moment, sir, is the source, is our source feeling any strain, or is it
no.
It's perfectly okay with it?
No. Practical, you are talking about the practical, right?
Yes, sir, I am.
No. It will not, there will be no problem. You can do this experiment, inshallah, when you will have the face-to-face thing. You can do this, is a simple experiment. You can do that.
Okay, sir. Thank you.
Okay, now here. So this is your 6.6. I have already discussed this one. Now your output voltage, when alpha will be 0, when the alpha will be 0, then output voltage will be VD is 0, 0.9 Vs, right? So what is the voltage we have lost because of the negative part of this one? That will be your VD. Alpha will be VD alpha minus VDO. So that is your 0.9 Vs cosine of alpha minus 0.9 Vs. When alpha equal to 0, then your this will come VDO, and that will be your 0.9 Vs 1 cosine alpha minus 1, right? That is the voltage, average voltage we have lost because of the presence of highly inductive load, and also if you delay the angle. If the angle is more than pi/2, what will be the voltage, average voltage? Positive or negative? If it is say 120 degree, then it will be positive or negative? Hey, you don't know. Cosine 120 degree is what? Minus half. Hello?
Yes, sir.
Yes, sir.
So your voltage, average voltage will be negative, and the current, if the current through the load is still positive, then your voltage power will be negative. That means it will reverse the power. It will feed back the power to the input. That will be the, I told you, you can operate your thyristor in 2 regions. Can you remember?
Yes, sir. Now we remember this.
So this is your inversion mode. This is your rectifying mode. Okay. Now go back to your main discussion. So yeah, that is the thing we have already done. We have already discussed these things. Okay, so this is the power they have already mentioned you. The output power, okay? Vd equal to 0.9 Vs cosine of alpha. Id is a constant for current, so Pd will be Vd Id. So that will be. I think there should not be any confusion about this, right or wrong? Okay. So now
Yes, sir.
we have already formulated this one. Vd equal to 0.9 Vs cosine of alpha. VDO, if alpha equal to 0, that's alpha equal to 0, that is 0.9 Vs. So Vd by Vd0 will be a cosine of alpha. Now, if you plot this one, then look here, you have to plot that with respect to alpha, then it is nothing time but the cosine where when alpha equal to 0, so you will get 1 here. When alpha equal to 90 degree, will get 0. When alpha equal to greater than 90 degree, will get negative, and when it is alpha equal to 180 degree, you get the negative minus 1. You understand it or not? So this one will be known as the rectifying mode, and this will be your inverting mode. You got it? Hello?
Yes, sir. Yes, sir.
Okay. That's nothing but the same. So you are doing a lot of complicated thing than this. Okay, now so look here. We have that current wave shape IS. We are very much concerned about this. Current has that rectangular shape because of the nature of the load. This is your alpha, this is your pi plus alpha, and this is your twice pi plus alpha. Yes or not? Am I correct or not?
Yes, sir.
And what is this one?
ID.
Capital A. Okay, so now, so what is the RMS value of this rectangular thing? Any idea? Rectangular wave, you square it and then take the average and divide it by
ID,
the
sir.
ID, sir.
capital A. Can you remember what is this IS1? That is the first harmonics or fundamental component from the diode case.
So the sine wave. Oh, yes, 0.980.
Right? Okay.
Yes.
Now, if we do the Fourier analysis of this one, then we will get, first let us concentrate on the fundamental component. Fundamental component will have the wave shape like this. Fundamental is the sign. Okay, let us look at this equation. This is the Fourier series. This one, first one is the first harmonic or fundamental. First harmonic or fundamental component. Why it is known as fundamental component? Fundamental. What does it mean? Any idea? Fundamental is that it will have the same frequency of your main things. So that means the frequency is going like this, right? If you start your counting of your wave shape, so that will be your this is nothing but the twice per time period, and frequency will be 1 by twice per. Am I correct or not? So in our country, the frequency is 50 hertz. So of course, the fundamental component will have the same frequency. That means, okay, it will be better to draw the, suppose this is 5. So this is the first thing. This is your voltage wave shape. Okay. So voltage wave shape and the fundamental component of the current will have the same frequency. That is why it is called the fundamental. Or if your input, if your current which you want to do the Fourier analysis, that however it will have that frequency, the fundamental component will have the same frequency. Okay. So can you remember displacement angle? Definition of the displacement angle. So this will be the phase difference between the Vs, that will be the sinusoidal voltage, and also the sinusoidal component of the current. Sinusoidal component of the current with the same frequency will be on the fundamental. So this will be known as phi 1 displacement angle. For our case, then what will be your phi 1 displacement angle?
Alpha.
Alpha. That means the firing angle. Okay. So then the power factor, input power factor, by definition, it will be a cosine of phi 1. So for our case, it will be cosine of alpha. You understand it?
Yes, sir.
So that we have already done this one. IS1 will be your 0.9 ID, and we have already know that one. How to find out the other RMS value of the other component? So since we don't have any even harmonic, then we can try to find out the third harmonic. So IS1 will be your 0.98. 0.99 by 3. IS5 will be 0.9 ID divided by 5. You understand? These are the RMS component. These are the RMS component of your current of the say. This one. This one is the why we are multiplying by root 2. Why we are multiplying by root 2 here? Can anyone tell me? So this is the peak value, right? Peak value. How to find out peak value? Peak value we have to
Multiply root 2 into RMS.
right. The root 2 multiplied RMS will give. So these are the RMS. Okay. Let us see the figure from your book. That will make it more understandable to you. You follow my pen. So this is your input voltage. This will be rectangular with your current, and the here, and the fundamental component will cross the zero crossing of the same. That means the input. So it is like this one. And the difference, the angle difference between the Vs that has the fundamental component of the frequency of 50 Hertz, and IS1 will have the frequency of the 50 Hertz, and it is also sinusoidal. So the displacement angle between cosine of phi 1, that is the zero crossing of the IS1 and Vs. Okay?
Yes.
Is it clear?
Yes, sir.
So they have plotted this one. This is nothing but the research point of view. So IS1 equal to IS3 by H. So sorry, IS1 by H. So IS8 by 8. Sorry, IS1. That will be 1 by 8. So you can find out a different component of the current. Like if you put H equal to say 3, then it will be IS3 by IS1, that will be 1 by 3. So this is the 1 by 3. The fifth harmonic 1 by 5. This one. Seventh harmonic. So why they have drawn this? Or why? That's the reason. The reason is that look, if we plot a curve here, we can see here the higher harmonics is diminishing, right? With respect to if this is the harmonic. So main component is the fundamental, and the second component is the third harmonic, and the third main component is the fifth harmonic. If we can filter out this two parts by using any Butterworth filter, Chebyshev filter, or your LC filter, filter design has to be done by you, and then your these non-sinusoidal rectangular wave current may look like very much close to the sinusoidal. You understand it, or you want that? You want that our current component should be this one, because you know that PAC, that means input power, will be your VS IS1 cosine of alpha. That means the power factor. So why we are taking IS1? Because this is sinusoidal and this one is sinusoidal. So we have to take both sinusoidal. Why we are not taking VS3 and IS5? IS3, sorry. VS5 and IS5. Can anyone tell me this? Answer this question. So in your PAC, why we are not, we have taken this one, because this is also one cosine of alpha, say. What?
Because both as VS1 and IS1 are sinusoidal.
That is why we have taken this one. But
Right.
why we are not taking VS3, VS5? Because VS3
Sir,
and
value is much less, not accurate.
no. For the sinusoidal, look here, for the pure sinusoidal, should there be any other harmonics?
No.
So VS3 will be 0, VS5 will be 0. You understand it or not?
Oh, so if our voltage was also a square wave, we would have
They're
taken,
right. But the voltage you are taking from the source,
right.
and it is sinusoidal, right? You got my point?
Yes, sir.
Okay. Now we'll see some of the equation first, then we'll come back to the figure. So here, total harmonic distortion. Total harmonic distortion will have this formula, and IS equal to ID, and IS1 equal to 0.9 ID, and IS 0.9 ID. And if you put all these things, that will be 48.43%. And is it not the same as your direct fan? Hello.
Sorry, sir, could you repeat it?
Is it not the same as your diode rectifier?
Yes, sir.
Total harmonic distortion. What is the implication of this total harmonic? What does it mean? It is 48.43%. Meaning is that it has been deviated from the sinusoidal by the percentage of this factor, 48.43. If our current is sinusoidal, suppose this is your IS, say, then what will be your, this IS will be the same, IS1 will be the same as your IS, right?
Yes.
Then the total harmonic distortion could have been 0, but we don't have this one. Unfortunately, our input current is not sinusoidal. That is why we have deviated. We have been deviated from the, because of the non-sinusoidal rectangular type input current. I hope you understand, right?
Yes, sir.
Then displacement power factor, we have already defined it. I have told about this one. Cosine phi. Okay, and what is the input power factor? That will be your displacement power factor. I'm sorry. Did I write down somewhere input power factor previously as cosine of alpha?
Yes, sir, you did.
Or it should be displacement power factor, okay? Okay, so input power factor will have the definition, this one. That will be 0.9 ID, and this is your ID, and this is your cosine of alpha. So ID cancels, so we will get 0.9. Okay, when alpha equal to 0, what will be your input power factor?
0.9.
So did you get that one for your direct rectifier?
Yeah. Yes.
Yes, you did. Because when alpha equal to 0, your output voltage will look like this, and your input current will have the resistance. Right?
Yes, sir.
Okay. Now, so this is your AC side power. I have already defined this one, and this is your DC side power. So if you are thinking about the lossless transmission, then you can write down then IS1 cosine of phi 1, that will be 0.9 Vs ID cosine of this is cancelled. Then here is cancelled. From here you can also find out IS equal to 0.9 ID. That we have already taken, right? IS1 is equal to 0.9 ID. You can also prove from here. If AC side power is equal to your DC side power, if you are thinking about the lossless transmission, then AC power must be equal to your DC power. And then you equate these two equations, you will get IS1 will be your 0.99. You understand what I say? Hello? Are you with me?
Yes, sir.
Okay. So there should not be any confusion. So the real power will be your this one, this equation. So okay, this is a constant, right? IS is constant, RMS value of the voltage is 0.9 is constant. So if we want to plot the P with respect to alpha, what should it look like? P, I want to plot P. Tell me something. Hey, what is the cosine alpha curve? Is it not the cosine alpha?
Yes, sir.
So this will be your P. Okay. What will be your S1? S1 is the reactive power. Vs IS1 sine of alpha, right? So Vs 0.9 ID sine of alpha. Now, if we want to plot S1, so this one is the peak value. Say this will be peak value 0.9 Vs ID, right? So what will be your S1 then? What will be the wave shape of S1?
So it will be just a sinusoidal wave
Right.
from 0.
Yes, I think peak value will be there. This will be 90. And this say pi. So right. You understand it or not? This will
Yes.
be your S1. And what is your S? S will be the reactive power VSIS. So that is your, so this will be like this, right? There is no alpha term. So this is VSIS. That is your ID also. This is VSIS. This is 0.9. This is your VSID, and this will be your 0.9 ID. Okay? Is it okay?
Yes, sir.
Okay, that has been plotted in the upper figure. If you go back and see that, look here. This is S equal to VSID. This one S1 equal to 0.9 VSID. And this is the peak value is equal to 0.9 VSID. And this is your S1. S1 is the cosine alpha. I hope you understand it, right?
Yes, sir.
If I set question from here, we will be able to answer. That we don't know, sir, right?
No, sir. Inshallah, we can, sir.
Inshallah.
Practice.
And also S1 can be derived from this one. And you know that from the power system, you know the real power square and apparent power square and root over that will be volt ampere square, and then actual power square. Q1 is the reactive power, right? So apparent power will be that will be your S1. That is, we know that this will be your Q1 square plus Q1 square. Q square P square is the real power, Q is the apparent power. You know it, right?
Yes.
So now, if I again go back and say something about this one. So suppose this is your alpha, and this is your pi plus alpha, where we are firing, and we see that the current is going like this, right? Can anyone tell me 0 to alpha which thyristor should be conducting?
The 3 and 4.
Okay, T3 and T4, right? And from alpha to pi plus alpha,
1 and 2.
T1 and 2. And again, after that, pi plus alpha,
3 and 4.
good. So the shifting of the current is going instantaneously, right?
Yes.
There is no commutative delay if there is no input inductance. So if there is no input inductance, so commutative, there will be no commutative delay, will be 0, and we have already, so far we have discussed. And actually, before your break, we have done until this. I have repeated this one because if I don't repeat, you will not understand anything today. So now we shall see the effect of the LS. Okay, I'm going back to our whiteboard again, so that will be easier for you to understand.
Sir.
Yes.
Sir, won't it be the same as just having diodes, just with the alpha angle?
Okay, let us see. The interesting thing, okay, sorry. Okay, yeah. So now we have to, our LS is not equal to 0. I'm plotting the figure. How much time we have left? 22 minutes, right?
Sir, 38, sir.
38, 22 minutes left, right?
Or, oh, sorry, sir. Yes, 22 minutes.
The thing is that actually, since I have to repeat our back things, this is the problem of the break. You understand? So you forgot everything, and this is also necessary to forget. Otherwise, you could have been traces. So this is your T1 and this is your T2, and this is your T3 and T4, right? And this will be your constant current. So, and this is your I. So now LS is there. I'm plotting. You try to minutely look what I am trying to tell you. This will be your input voltage. Okay, now we have fired here alpha. Also, we have fired here pi plus alpha. You got my point? So can anyone tell me this firing pulse will be given where? This one.
Sir, the firing what? Sir?
This firing pulse will be given to which thyristors? This one.
3, 4, 1. So 3 and 4, sir.
Right. And this one, the first one?
1 and 2, sir.
Right. The black one is the 1 and 2. You understand very nicely. Good. Okay. Let us start here. So thyristor T1 and T2 already forward biased with this positive voltage, but we have not applied any pulse between 0 to alpha. We have applied a pulse here. Okay.
Yes.
Now let us plot the current of IT1 and IT. This is your say IT3 and IT4, and this is the current. IT1 and 2. Okay, and you already told that. If there is no LS, we have already seen it also. Sorry, this is your phi and this is your phi plus alpha. So that was the current, right?
Yes.
Am I correct or no?
Yes.
And also here, this is twice pi plus alpha. So this kind was a negative current, right? Let me change the color. And here the current was like this. And here, of course, 0 to alpha, T3 and T4 will be conducting and the current is negative. When LS was 0. Now, this current, oh, I'm sorry. Because we are talking about the current. So, in the T3 and T4, the current should not be in the negative, right? We have to plot like this. You understand what I want to say? This is IT3. We are not talking about IS. Rather, we are talking about the current through T3 and T4 and T2 and T1 and T2.
Right,
You
sir,
got
right,
me?
sir. Yes.
Okay. So now, this current should have go to 0 and this current should have go to ID. So the total current here is always ID, right? But
Yes.
because of the presence of this LS,
Doctor.
this current will take some time to fall down. Because this LS will not allow this current to fall down immediately, rather than it will take some time. You understand it or not?
Yes, sir.
Okay, here also, this will take some time. So that if you if you add this current and also this current, the total current will be always 0. Suppose you are here, say this is your 10 ampere. So this one is 10 ampere. Then IT1 and IT is equal to 0.
Yes, sir.
Then when it is 5 ampere,
That
the
will be
IT1 5 ampere too, right?
yes.
And when it is 10 ampere, then of
That
course
will
the
be
current will
0.
be 0. So this way the commutation will occur. So this angle will be known as the commutation angle, right?
Yes, sir.
So now can anyone tell me alpha 2 with this range, which thyristors are conducting?
Sir, all four, sir.
All 4 thyristors are conducting. If, okay, particularly if these 2 are conducting, then what will be your VD?
What will be the VD? Sir, should it not be VS?
Why? Because you apply your Kirchhoff voltage, no? Negative, positive, then you are coming back here, short circuit.
Oh,
What should be VD?
0, sir.
0, sir.
Right?
Yes, sir.
So we will not get any voltage here. Will not get any output voltage. But in the previous case, when LS was not 0, we got the voltage. But we have lost this voltage because of the commutation. Okay. And then when the commutation is finished, then T1 and T2 is carrying the full current. Then we will get the, okay, let me,
Voltage.
yes, we will get the voltage, blue line. We'll get the voltage like this. And here again, the same thing will happen. It will fall down like this and the current will build like this. Okay. This is your pi plus alpha. And this angle will pi plus alpha plus u. You got my point?
Yes,
This
sir.
is your u. So during this period again, there will not be any voltage here. And then you get like this angle. So twice pi to twice pi plus alpha will be the equivalent to 0 to alpha, right? This is the, look here, this is the starting of a cycle. So this is also starting of a cycle. You understand it or not? You understand this part,
Yes, sir.
0 to alpha. It will be the same as twice pi to alpha. So during this period, T3 and T4 are conducting. During the commutation period, T1, T2, T3, T4 all are conducting. During this period, again, T1 and T2 will be conducting. During the commutation period, T1, T2, T3, T4 all are conducting. And during after the pi plus alpha to twice pi plus alpha, then again T3 and T4 will be conducting. You got my point or not? All.
Yes, sir.
Okay, now what we want to do? We want to find the commutation angle. Okay, so how can we find out? So during the commutation, say during the commutation alpha to alpha plus u, this is your commutation period. Commutation period. So all thyristors are T1, T2, T3, T4, all are conducting. Then we can write down the equation Vs equal to VLS. Am I correct or not? Because this is short circuit. Same thing as diode we have done, right? You are not, are you confused? Hello? Hello?
Hello, sir.
Are you-
No, sir, it's very similar to the diode concept.
Yes, right. So now LS, BIS, then it will be root 2 GS. We have already appeared the midterm exam. So I have multiplied this one by omega, and that will be omega t. And then if I integrate it, alpha to alpha plus u. So this is nothing but this area. Am I correct or not?
Yes, sir.
This area AU. And the operator was omega t. Now here operator is IS. So what is the current at omega t equal to alpha? Look here. Oh, okay.
Sir, 0.
Yes, 0, right? IS. I want to plot the IS now. IS will have that wave shape like this. You got my point? This is your IS.
Yes, sir.
Minus ID and this is your plus ID, right? So what is the current at omega t equal to alpha? This is your alpha. This is your alpha.
Sir, 0, sir.
So 0. Put it there. No. No. Sorry. Was it? Sorry. I'm sorry. This was not correct. It was not correct. Let me plot it. What is the current here? No, sorry. What is the current here? Was it not ID? Minus ID? Because T3 and T4
Right,
was
sir. Minus ID. Yes.
right. So now here, this will be going like this. Am I correct or not?
Yes, sir.
So, and then it will be
Going straight up to
5 plus
pi,
alpha.
5
5
plus
plus
alpha.
alpha.
Yes, and we'll go
Then
down
again it,
up to the next commutation.
yes. So look here, it is the zero crossing of IS is between your alpha to alpha plus u. This is your alpha and this one alpha plus u. This one is nothing but the u, right?
Yes, sir.
So now, what is the current at omega t equal to alpha? Minus
Minus
ID.
ID, sir.
And this is your plus ID,
Plus
right?
ID.
And if I now complete the integration here, that one will be your, this will be of course AU. So AU is coming as 2 omega LSID. And if you complete the integration, that will be your root 2 GS. Then cosine of alpha plus u minus cosine of alpha. Am I correct or not?
Yes, sir.
So And if there is no LS, so we got that VD alpha equal to 0.9 Vs cosine of alpha, right?
Yes, sir.
When the LS is there, so we have lost this area, A2, sorry, area A. We have lost this area. So we have to negate this area and divide it by to get the average. What will be the dividing factor?
Sir,
Pi.
pi, right?
So that is the same as your
Yeah.
that only cosine alpha is there. So, so this is the expression of your average voltage, and this is the expression for your to calculate that if you know alpha, if you know omega, if you know LS, if you know ID, then you can find out the commutation angle. You got it or not?
Yes, sir.
Okay. Now I'm going to the book again. Okay. So here, can you see the book?
Yes, sir.
Hello. Okay. Now look, this is your Vs as usual, sinusoidal, and the current wave shape is like look like a trapezoidal. This is your, you know that this is your, this point is equal to alpha, and this point will be your alpha plus u, and the commutation period is u. You understand?
Yes, sir.
And the current zero crossing of the trapezoidal current is between your u, and of course your IS1 will cross the same crossing point. So we can say that your now the displacement angle will not be your alpha rather than what? Alpha
plus
and
alpha.
yes, in between in the middle point, approximately in the middle point. So
Right.
now this is your displacement angle, and displacement power factor will be your cosine of phi1 and then cosine of alpha plus 2/2. Okay.
Yes, sir.
Okay, good. And now then we can always move forward. And as I have already shown you, this is the wave shape of your voltage, and we have already found out the expression of the voltage Vs cosine of alpha minus 2 omega SID by pi, right?
Yes, sir.
We have already found this. Okay, good. So that they have drive this one, I have already done. And what is the voltage we have lost? The area we have lost, that has been here. This is also given. I hope you understood this, what I want to say. Okay. Then let us go back a little over, down. See. So this is the video we have already found, right? Did
Yes.
I not already found this one?
Yes, sir.
Okay, so let us study a problem. This problem is very, very important. Sometimes I set this problem in the exam. This is the example. So it is mentioned that for the this is a converter, control rectifier for this one. How many students are here? 37, right?
7, sir.
38 including me.
Yes, sir.
Okay, so this is your IP. So it is mentioned that this converter ALS has a 5% per unit value. It is written in the rated voltage 230 volt, RMS value 230 volt, VS 230 volt, and 60 hertz, F equal to 60 hertz, and the volt ampere VS IS will be your 5 kVA. Calculate the commutation angle, and you have to find out the When you will put LS equal to 0, then it automatically reduces. And the power absorbing power with the rate of input voltage, the VS LS has to be calculated, and the output power is 3 kilowatt, and firing angle is 30 watt. We have to study this. Okay, here your rated current can be find out because this is your volt ampere has been given VSIS. So this is this one. So you can always find out your VA, right? Your VA. From that you can find out the rated current. You understand it?
Yes, sir.
And then with that one you can find out the base resistance that will be rated voltage given by rated current, and that is coming as ohms, 10.58 impedance. Okay. So we got that base resistance, and then it is written that the inductance will be 5% of the base. So 5% multiplied by Z base and divided by omega, right? Because omega L is equal to Z, and that will be your 0.05. So from there, LS can be calculated. Z base we have calculated 0.05. What is the Z base we have calculated? 10.58 divided by omega equal to 2 pi x to the 60, and it is 1.3. This is the main text we have to find out first. Do it first, LS, and then we can proceed like the power we know. The power is VDID. This is given already, 3 kilowatt. VD is equal to your 0.9 PS cosine of alpha DD minus 2 omega LS ID by pi. So that they have written and multiplied by ID. If you do that, your VD. So ID square, that will be 3 kilowatt. This is a quadratic equation. If you take the realistic value, then it will be 17.3. So we know that AU will be 2 omega LS ID equal to cosine of root 2, right? Root 2 VS. Is it root 2 VS? Then cosine of alpha plus U minus cosine of alpha. Am I correct or not?
Yes, sir.
I have to check, double check. Just wait 1 or 2, 3, 4, 5 seconds. Yes. It will be, sorry. Let me write down. AU will be 2 omega LS ID. Then that will be your cosine of alpha minus cosine of alpha plus U will be your, so will cosine of alpha minus 2 omega LS ID divided by root 2 VS. So this is your equation number 6.24. Okay. So alpha equal to 30 degree, omega twice pi f, LS equal to the millihenry we have already found, 1.4 millihenry. You have to convert it to Henry. ID we have already found, so 70.3. VS equal to 30, and with that one, if we put that, then we will get the delay angle of the commutation angle equal to 55.1. And VD, if you substitute the VD equal to 0.9 VS cosine of alpha minus 2 omega S ID by pi. So everything is known to you, and then if you do that, then you will get the VD. Okay, is it clear?
Yes, sir.
Let me take quickly your attendance because you have the, what is you have? You know, what time you have the quiz?
So 2 o'clock.
2. Let me take the attendance. What is the time? Already 1?
Yes, sir.
Okay. Let me quickly, I have some technique to quickly take your attendance. I am applying for 1. So we will get another 2 classes, inshallah, right? I hope I will be able to complete.